So this I hope is clear to you. So what is
Yes.
the wavelength of the matter wave? What is the wavelength of the matter wave? Can you tell me?
The formula?
Which de Broglie gave. It is lambda equal to
Yes,
h
sir.
upon p. Okay,
Yes, sir.
h is the Planck's constant and p is the, what is p? P is the
The
linear.
P is linear.
I can write it in this way also, lambda equal to h upon mv. Got it?
Yes.
Mv is the p linear momentum. All the units are in SI units. Okay, h is 6.626 into 10 to the power minus 34 joule second, and the mass you should take it in kgs, and velocity you should take it in meter per second. Is it clear? So
Yes.
suppose, and I have also shown you in the last class, I have shown you that this uh, this wave nature is insignificant for day-to-day life particles. Is it clear? This wave
Yes.
nature doesn't have any significance for normal day-to-day life particle, just like the example which I took. I took an example of a ball, okay, which is too heavy in terms of as compared to your electron, proton, and neutron. Electron, proton, and neutron are very, very small. Okay, its mass is
Yes.
0.1. And if you try to figure out what its wavelength is, its wavelength is very, very small, 10 to the power minus 32. Got it?
Yes, sir.
Okay. So this wavelength is so small that it is insignificant. This wave nature is insignificant for large objects.
Mm.
What is the reason, you will say? What is the reason why it is insignificant? Because
Noticeable.
their wavelength is too small. Because their wavelength is very, very small. This we have discussed in the last class.
Yes, sir.
So wave nature is insignificant for large object because of their very small wavelength, but it is significant for
The subatomic.
it is significant for subatomic particles. Why it becomes significant? Why is it so?
Oh, because like the yeah,
Because of their very,
that's
very
it.
small mass. Okay. because of their very, very small mass. Okay. The wave, small mass if you have, okay, if you take small mass, this value will be large.
Mm.
Okay. Lambda will be large. And if lambda is large, the wave character is significant. Got it?
Yes.
So very important thing. Okay, so as you are having more and more mass, the wave character become insignificant. And if you have small mass, the wave is bigger and the wave nature is appreciable. Okay. It is, for example, if you have to see for electrons, protons, and neutrons. Similarly, remember one Bohr postulate is in that Bohr was unable to explain that postulate. That postulate said that the electrons can move. Can they move in any orbit around the nucleus?
No, sir.
Or are there
Yes.
certain permissible orbits? Was there a condition set, a condition applied for the orbits?
Yes, sir. There's condition.
What was the condition for to choose the
Mm.
orbit of electron?
Only those orbits are permissible in which the Bohr's model.
Hmm. So we had seen only those orbits are permissible
Sure.
where the angular momentum of the electron is quantized. Okay, we have seen this.
Mm.
So angular momentum is integral multiple of what? H upon 2
8
pi.
by 2 pi.
Got it? So what was the actual
Yes.
reason for it? What was the reason? What was the actual reason? Integral multiple. H upon 2 pi means in the first orbit it is H upon pi. In the second orbit it is twice of H upon 2 pi. In
Sorry,
the third
your
orbit,
voice is breaking.
yeah, you can check your connection because my connection is okay. Just a second. Is it clear now?
Yes.
The video is stuck in.
Yeah. Yeah. Good evening, ma. Am I audible?
Yeah.
Okay. So we have just started, and what we were telling, I summarized uh, with Nabila that wave nature is just like day-to-day life objects also have the wave character. And de Broglie he uh, discovered the formula for the wavelengths, okay, of the matter waves, and it is lambda equal to h upon mv that we discussed, and it is meaningless for large objects because the wavelength is very very small. That's what I told Nabila just now. Okay, this is what is written. But for small particles, very very small particles like electron, proton, and neutron, the wave nature is very significant. Got it? It is very significant for small particles. That's what I discussed with Nabila just now. Okay. So now just I started few seconds back, and you entered the class at the right time, and that is application of de Broglie game. Okay. So suppose if the electron is like this is the particle nature. Got it? And if it is a wave, it will be like this. Is it clear? Right? It will not be present at one point. It will be present at simultaneously, it is present at many places. Is it clear or not?
Yeah.
So what is the application of de Broglie's lemon? So normally this is normal, common man cannot think of this. We can't think that particle, this pencil is having a wave nature, means it is not here, it is here also, it is here also, it is here also. Okay, we can't see because, but you can't see pencil here or there. You can see it only in my hand because its wave nature is insignificant, it is negligible. Okay, if I apply the formula, if I write the mass lambda, and if I calculate its wavelength lambda equal to h upon mass into velocity, if its mass is too large, so its wavelength is going to be too small, very small wavelength, means it is not here or
So I
there.
didn't understand the pencil example.
Pencil example means this pencil is it is a particle, it is a
Yeah.
wave. If it is a wave, it can be present here also, here also, here also. Okay, because wave is not present at one point, it is present at many points.
Oh, like
Just
that.
like
Okay.
when you throw a stone in a pond, what happens? Waves are generated. Got it? Of water. So do you find the waves at one point or at many places?
Many places.
Many places, right? So if this is having a wave character, it should be at many places, but you can't see it at many places. You can see it just in my hand because its wave nature is insignificant. Its wavelength is very small. Got it? It's a large particle. Nabila, is it clear? Maha, is it clear?
Yes,
Yes,
sir.
sir.
Because their wavelength is very very small. Very small wavelength means it's not spreaded, so it is just at one point. You can, for large particle, you can assume them to be behave like a particle nature. They show only particle nature. Their wave nature is insignificant. That's what I told. Okay, but for subatomic particles like electron, proton, and neutron, because their mass is very very small, very small mass, so wavelength is going to be very large. So electron will have a very large wavelength. Got it? Is it clear? So electron will have significant wave character. Okay. Is it clear or not?
Yeah.
Yes, sir.
Suppose if an electron is moving, if a proton is moving at the same velocity, Which one is having a larger wavelength? Electron is having, yeah. So if particle is like this. If we think of particle, this is the electron. We say that okay, this is the electron which is going. Okay. Normally we think it in this way only, because normally we think like a common man, right? So, but actually it is a wave. Is it clear? It is moving through the space like that. Means it is not present at one point. It is wave, means it is a form of energy which is spreaded. Is it clear? Similarly, proton if it is moving. So which one is having a longer wavelength? Electron or a proton? Why?
Proton.
Which one is having a longer wavelength? This is the wavelength.
The electron looks.
Yeah, it will having a longer wavelength and proton will having a shorter wavelength. Why? You said it in this way. Right? That is correct. Answer is correct. But why? The velocity is same, right?
Maybe because
Because
protons and neutrons are bound together, right? But electron is freely in the orbit.
no, I'm talking about the wave character. Yeah, that is true. That is with respect to their position in an atom. Okay. But if I talk about the wavelength, okay, this is lambda equal to h upon mv. H is constant, velocity is same for electron and proton. Got it? So which one is having a longer wavelength or shorter wavelength? If the mass is more, proton the mass is more. Proton is 1826 times the mass of the electron. Got it? Is it clear?
Yes.
Sir, can you repeat?
The mass of proton is nearly is it clear or not? Proton is 1826 times heavier than electron. Okay. So which one is having larger mass? Proton. Electron is having smaller mass. Got it? Is it clear or not? So if
Yes,
the mass
sir.
is more, the wavelength is small.
So, sir, the lesser the mass, the more the wavelength.
Yes, because it is in denominator. So de Broglie's wavelength is inversely proportional to the mass of the particle.
Okay.
And that's why we say that a day-to-day life object doesn't have any wave nature. So their wavelength is very small, they are very large masses. Now we need to talk about the application of de Broglie's wavelength in quantization of angular momentum. Right? Actually, we discussed one Bohr's postulate, if you remember. That Bohr said that electron can't move in any orbit. It can move only in selected orbits. What was the criteria for those selected orbits? What was the criteria for those selected orbits? Hmm? Yeah, only those orbits were permissible where the angular momentum of the electron is integral multiple of h upon 2 pi. Got it?
Yeah.
Okay. The first orbit, it should be h upon pi. H upon pi is constant. H upon 2 pi is constant. Okay. Momentum should be, angular momentum is the mass of the electron, velocity of the electron into radius of the electron. it should be integral multiple of h upon 2 pi. Only those orbits can be used by the electron to move around the nucleus. But Bohr was unable to explain why this is happening. Okay. Even I also told that this is the drawback of the Bohr model, that why this quantization was happening. Bohr was unable to explain. But he told that this is the thing which he has observed. But what is the root cause for it? We don't know. But now we know. Is it clear? By applying, now we know that the electron is not a particle. It is not like a grain of sand. It is actually a moving wave. Is it clear? Moving wave of.
Yes.
So if it is a moving wave and if it is moving around the nucleus, okay, so suppose this is the particle nature of the electron. This is just a particle. Okay. And this doesn't put any limits to the selection of orbit. Okay. But if you choose this electron to be a wave, got it, then it puts a limit on the selection of the orbit. Okay. So suppose if it is a wave, I am drawing the wave on this orbit. So how many waves I have drawn? This is complete one wave.
Three waves.
Yeah, two. This is the second wave, because the wave actually one wave is this. Okay, this is one complete wave. So this is second, and this is just half of it I have drawn. Is it clear? So this is 2.5 waves. Is it
So
clear?
is this like a random drawing of the wave, or is this how the wave looks?
No, how it looks, that's what we are trying to figure out. Okay. Actually, actual details are discussed in the later part of the chapter. I'm drawing the wave in a very simple manner. Okay, just a normal wave which we draw. Okay. I'm trying to explain that electron is a wave, and if it is moving around the nucleus, okay, it will have a wavelength, right? And how many waves should it make? Is there any number to it? Is there any limit to the number of waves which electron can form? Is there any limit to it or not? Hmm. So how many waves are drawn here? Can you figure out? Okay, this is the path of the electron. If I represent the electron as particle, I will write E. Okay, and or I can just put one dot. Okay, till now we were looking in this manner only. Electrons were assumed to be particles. Got it? But now, from now onwards, we came to know after studying this deep Broglie wavelength of the matter waves, we came to know that electron is not a particle, but it will also have a significant wave character or wave nature. Got it? Because it is a very
So
small.
how are you counting the waves?
Yes. So, how many waves are there in this first diagram, and how many second diagram? How many waves are there? That is clear. I will count it in first diagram. Okay. So this is one trough and one crest. Is it clear? From here to here, you have just one wave. Got it? Agreed?
Okay.
Then you have the second wave being starting. This is the second wave trough and then crest. It get completed. Okay? Clear? Nabila, is it clear or not? Because this is
Yes, sir.
one. You take it.
So the points that you mark, the lines, that's one wave.
Got it? And this is actually, I have just putting a cut mark to represent that, to count the wave, to keep the track of number of waves. Okay, and this is the third wave. So do you agree with it? There are three waves in it. Do you agree with it or not?
Yeah.
No, as per the diagram. Okay, how many waves electron will make? What is the actual thing? That we will discuss later on. Okay, as per the depiction, if the electron is wave, it is like this. Okay, and it is moving in a circular orbit. The first diagram, the electron is making three waves. Clear? And in the second diagram, it is making 2.5 waves. Got it? Agreed or not?
Yeah.
Okay. So now, Maha and Nabila, now we can move ahead. Where do you think the wave will lose its energy and it will get cancelled? Cancellation of waves happen. Where do you see cancellations of wave happening? You see it on your seashore. When one wave is moving towards the shore and it hits another wave which is going away from the shore into the sea. Okay, you might have seen it many times. Okay, you have this cancellation of waves being applied in noise cancellation earphones. Okay, uh, that is the two things. So as per the diagram, where do you think the wave can get cancelled and where do you think the wave will not get cancelled?
Maybe when they meet the other wave.
Yeah, in other way, but it should meet in a proper manner so that they can get completely synchronized with each other. Are you getting the point? But if they are actually meeting it in this way, one is crest, another is trough, okay, they are going to lose their energy and they're going to undergo cancellation. So in the first diagram, do you observe that the waves are getting cancelled, or in the second diagram, do you observe that the wave are going to get cancelled?
First wave.
First wave, you look. Actually, I have drawn complete three waves, okay? And the where one waves end, another wave start. So they are actually superimposing on each other completely in a proper way. Okay. But in this case, if you look, this wave is trying to move up and they are not actually getting completely joined together. Are you getting my point or not?
Yeah.
Okay. So can you have this kind of wave? This kind of wave. Can you have it? There is a cancellation happening. Got it? It will look like this. Or you can have this kind of wave. One wave is like this, another wave is like this. This is the more proper way. Whole wave will get completed. Okay. So actually you see that the waves are getting cancelled in the second diagram, and this first diagram is okay. This is incorrect. The electron wave will get cancelled. It will lose its energy. It will change its path. Okay. It will lose its energy in the form of photon. Got it? Here, it will change its orbit. So only those orbits are permissible where the electron make the complete waves. Because if the waves are complete, they are not going to lose their energy. So with that, I'm going to derive the formula for quantization of angular momentum. Okay, what is the circumference of the path? 2 pi r is the circumference. What is the circumference of the orbit? 2 pi r. Okay, and that whole circumference should fit in either one wave, two wave, three complete waves, okay, or four waves. It should not be like that 1.5 waves, because if that 1.5 wave, they are not going to superimpose properly and they are going to lose their energy. Are you getting my point? There is a clash happening in the waves. Got it? Can you see? Maha, Nabila, tell me.
Yes. So
So
decimal ones will cross together
yeah,
and
so
the whole
this is
ones won't.
actually, yeah, this is actually perfect blend. The whole wave is actually uh, getting completed. Okay, so if the electron is making this kind of wave complete whole number of waves, it will, the wave of the electron is going to persist in that orbit. Got it? And if the electron, the path of the orbit is such that it is not going to, and the velocity of the orbit is such that it is not going to make a perfect whole number of waves, then this wave is going to lose its energy, and that path will not be taken by the electron. That will not be considered as the orbit of the electron. Any doubts on this? Maha, Nabila, any doubt?
No, sir.
Okay. So this Bohr was unable to explain because Bohr was not aware of the wave nature of the electron. Bohr was only aware of the particle. Bohr thought that electron is a particle, okay, just moving around there. Okay. So if we think of particle, we, this thing will not come into our mind, right? And 2 pi r is a circumference. Okay, that circumference, whole circumference should be such that it should hold some whole number, total fix some whole number complete waves. Okay, the circumference should not be more than n lambda, so it should not be less also, right? Otherwise the wave will not fit into that whole path and they will lose their energy, they will cancel each other. And now we know what is lambda. This lambda wave is the wave of electron, which is a matter, and its wavelength was given by de Broglie, h upon its momentum mv. Is it clear?
Yes,
So
sir.
now we, if we cross multiply mass into velocity, it will be equal to nh upon. Got it? So this is how the quantization of angular momentum was derived. Okay. So actually, okay, Bohr said directly this formula but was unable to explain what was the root cause of this. But after knowing that the electron is not the matter, it is not a particle, it is also following the wave. It is like a wave. So we should also agree to a point that the whole path, whole circumference should hold that some whole number of waves in lambda. So with that, and when lambda is the wavelength of the matter wave, d Broglie wavelength of the electron, which can be calculated by taking h upon mb, and if you cross multiply, we get up to the formula which Bohr gave. Okay. So now we know what is the real reason behind the quantization of angular momentum. The real reason, Nabila, is basically the wave nature of that. Is it clear or not?
Yes, sir.
But Bohr was not aware of these things. Bohr directly gave this formula. He observed that okay, there's something like this is happening. He directly gave this formula. But why this is happening, Bohr was unable to tell. Next is, so this is the application, the actual application of the wave nature of the electron. That electron is not behaving like a particle, it is behaving like a wave. And actually we can see it in Bohr model also. Now there is one more thing, Heisenberg uncertainty principle. What is this Heisenberg uncertainty principle? Any idea if you have heard of it in the school? Nabila, any idea?
Sounds like a place name.
Pardon?
It sounds like a place name.
Okay, some place in Germany maybe. Yeah, these Heisenberg and these are German people, right?
Yeah.
Okay, so Heisenberg uncertainty principle. HIESN, Heisenberg. Okay, uncertainty principle. So basically, if electron is a particle, okay, if it is a particle, its position, because it is a particle, so its position, velocity, momentum, position, position I have already written. So radius of the orbit. So what it means, whatever I have written, what it means, Nabila.
There's a formula for radius, right?
I think it's
Is
saying
it?
that with the help of position, velocity, and momentum of the particle, we can find the radius of the orbit.
Yeah, radius of the orbit, and the Bohr has already given the formula, right? 0.529 into n square by z angstrom, right? The Bohr radius. okay, of any unielectronic species. Bohr calculated the formula. Bohr also gave the formula for the velocity of the electron, the radius of the orbit. Okay, all can be did. If it is a particle, and you have done it in your ninth class also. If I throw a ball with velocity, if I drop a ball, okay, from my hand, after how much time it is going to hit the floor, okay, after 1 meter, what its velocity is going to be. You know the formula is S equal to ut plus half at square, v square equal to u square plus 2as. You apply it in physics, okay, right? You are
Yeah.
quite familiar with these formulas. So that ball is the particle, okay, it has fixed position. You can't say that ball is here also, there also, okay, it is not behaving like a wave. So you can determine its position, you can determine its velocity, you can determine its momentum accurately with absolute 100% accuracy. Is it clear?
Yeah.
Because it
Yes.
was behaving like a, it was behaving like a particle or a wave. What should I write? Because it was behaving like a particle. For a ball I am talking about. Got it?
Yeah.
So it can, you know what are the formulas need to be applied. Okay, you apply and you find the velocity, you find the path of the ball, and all things, sort of things you are going to calculate in your physics, because that is a particle. I am behaving like a particle. You can see me sitting in front of the camera, okay, and just one, not many, because I am behaving like a particle. My mass is too big to behave like a wave. But suppose if I acquire a wave nature, so you will see me here also, you will see me there also, or in some other room also, part of my wave is there. So I will not be placed only at one point, I will be at many points, okay. That's what wave nature is, okay. So now, because as we know that these subatomic particles have significant wave character, so it is impossible to determine, because of the wave character, you can't say that this is the particle. You can't pinpoint it. You can't determine its position with absolute accuracy. Got it or not? If you have a wave nature,
Yes, sir.
because of the wave nature, it is impossible for us to determine simultaneously the position and momentum of the particle with absolute accuracy. So if it is a wave, it is like this. If I ask you where is my electron, can you pinpoint its location? That here it is. Or will you say that it can be present somewhere from here to here, there? Can you pinpoint its location if it is having a wave nature?
No.
Yes or no? You can't pinpoint. Because the wave cannot be at a one point. It is simultaneously present at many points. So obviously this actually, because of the wave character, it brings in the uncertainty in position. Is it clear? You can't say that
Yes.
electron, I can't say that, oh, this is my electron. No. Here I can say, okay, this is my electron. Right? I can fix its position. I can say, okay, my electron is somewhere here to here. Okay, because that is the reason where the wave is actually present. Got it?
Yeah.
Is it clear? So
Yes, sir.
it is there is uncertainty in position due to the wave nature. You have seen uncertainty in position, and if you have an uncertainty in position, obviously there will be uncertainty in momentum, velocity. Everything will become uncertain. Okay, is it clear? So are you getting the idea, basic idea behind the uncertainty principle?
Yes, sir.
Yeah.
That it is because of the wave nature, we can't pinpoint the position of the electron. Okay, so we can't pinpoint its velocity, because if the position is not known, how you will calculate the distance traveled and velocity. Okay, so you can't have fixed values of position and fixed values of velocity for an electron. What is the root cause of this uncertainty? What is the root cause? Root cause is,
The wavelength itself.
yeah, the wave nature itself, right? It is not because something we don't know. We know now, and we know now that it is having a wave. So we can't have fixed position, fixed velocities, fixed momentum. So Heisenberg uncertainty principle says that it is simultaneously uh, impossible for us to determine the exact position and the momentum of the particle. Okay, momentum means velocity of the particle with absolute accuracy. So always the uncertainty in position. This is the uncertainty in position. Okay, this is, means you say that the particle can be from here to there. So always Heisenberg also gave the formula. Okay, so this is the uncertainty in position. And because of this uncertainty in position, there will be some uncertainty in velocity also. Okay. And there will be some uncertainty in momentum also. Uncertainty in momentum is because of momentum is m into v, and because the particle can be here or there, so you will have some uh, variation of the velocity also, because you don't know the exact distance. Okay. So you have uncertainty in velocity also, right? Delta p equal to m into delta v. This is the uncertainty in momentum. So Heisenberg gave the formula. So uncertainty in position into uncertainty in momentum will always be at least will always be at least, or it will be more than h upon 4 pi. The error in position and the error in velocity, momentum, or it can error in position, error in velocity is greater than equal to h upon 4 pi m. For the purpose of calculations, we take it equal to we take it equal to h upon 4 pi. Okay. But normally the uncertainty is more than this. To keep it minimum, we take it h upon 4 pi. Mass I have cross multiplied and I have taken it on the denominator side, on the right hand side. Is it clear? So it is impossible to get the exact velocity because you don't know the position. So how you will get the exact velocity? So that is inaccurate, and the velocity is inaccurate, the position is inaccurate. Okay, so everything is inaccurate. So at least we should have some idea. Okay, so Heisenberg told that the uncertainty in velocity and position, momentum, should be greater than equal to h upon 4 pi. This is known as Heisenberg uncertainty principle. This x is the uncertainty in position, and delta px is the uncertainty in momentum due to uncertainty in velocity. Right. So let's do one problem. So this is insignificant. This is useless to discuss for day-to-day life objects which are very large. If the object is very large, you will have a very small wavelength and you will not have any wave character in it. Okay. If you don't have any wave character in it, you will say that okay, this position is fixed. If its position is fixed, you can calculate the velocity with absolute surety. Is it clear or not?
Yes.
Yes, sir.
So let's now do some problem related to Heisenberg uncertainty. So now we have to, but one thing is sure, if I say it in a very common man language, now we have to get rid of the image of electron being a particle moving around the nucleus in a circular manner with fixed radius and fixed orbit, with fixed velocity, which Bohr gave. Okay. Now we have to get rid of that concept. Okay. We are actually moving towards the wave mechanical model of a matter. Okay. And these are the two concepts, de Broglie's wavelength and the Heisenberg uncertainty principle, which are being used. Okay. So let's do a question, a golf ball. Oh, so an object of mass 40 grams and moving with a speed of 45 meters per second. So this is like a common life example, something having mass, some stone phone, and it is moving with a speed of 45 meters per second. If the speed can be measured within the accuracy of 2%, calculate the uncertainty in its position. So what is the uncertainty in speed? Ninety one hundred point nine meter per second. So the speed has, it can be 45 plus minus 0.9 meter per second. Means it can be lower or it can be lower than this, or it can be lower by 0.9 or higher than 45 by 0.9. That is the uncertainty in velocity. So what is the uncertainty in position? I mean, suppose if there is some up and down in the velocity, definitely there is up and down in the distance traveled also. Getting my point or not? So uncertainty in velocity will cause uncertainty in position also, right? But it is not in common life example. It can be because of our limitation that we are not able to calculate the velocity correctly. But in the subatomic world, this is because of this is because of the wave nature. Is it clear? So because we are talking about the wave nature, it is because of the wave nature. So we are going to apply Heisenberg uncertainty principle. Okay. So which says the uncertainty in position into uncertainty in velocity or momentum. Initially, the Heisenberg gave the formula for the momentum that was greater than equal to h upon 4 pi because it is velocity. So h upon 4 pi m. Got it? Is it clear? Right.
Yeah.
So now we have uncertainty in velocity is already given in the question, that is 0.9. Okay. Uncertainty in position is asked. We just need to put this formula, and for calculation purpose take it equal to take the equal to sign. instead of greater than equal to. H is 6.626 into 10 to the power minus 34. 4 pi is 3.14.
So we can take it as 6.63, right? To make the calculation easy.
Yeah, you can take it, right? And that mass is basically, mass is how much? 40 grams. So 40 gram is 0.04 kg divided by 1000. Take all the things in SI units. Okay, this is 6.63. Got it? So delta X, if you calculate, right, take it on the, take this 0.9 in the denominator side. It is 6.63 into 10 to the power minus 34. At least put the value in the exams, okay? In the school exam, put the values. Okay, so that you don't lose the marks. And if you calculate, it will come around 1.46 into
So
10 to
do
the
we
power.
really need to calculate this?
Yeah, you have to calculate if the question appears. Right? But normally in the competitive examination in NEET, okay, they don't actually rely on this type of calculation. Okay.
They don't ask this in NEET?
Actually, they give you the in the form of general formula. So I can take one example from NEET also. So that can help us to understand what type of questions are being asked in NEET. This is clear, Nabila? Uh-huh.
Yes,
Yes.
sir.
Okay. So just you need to remember first, but you need to remember the formula. These formulas are very important. And the one thing is these formulas are such that we can't derive them. Okay, these are not thing which can be derived by common sense or something, because this is quantum mechanical model of an atom. Okay, so very tricky things. And these people, Heisenberg and De Broglie's, actually they have done quite a lot of study, right? So we need to remember this formula, and the formulas are very small. Okay, so we can take some neat question, very simple. They actually test the concept. They don't test your mathematical calculation part. Okay, so let's do this
So they
question
will
is
only
also,
ask theory wise.
pardon,
So they will only ask theory based question.
neat
Yeah.
theory based, actually some little bit of numerical based on understanding of the concept. Okay, for example, suppose if you have reason assertion question, they look quite easy, but they are very difficult. One should be thoroughly aware about the whole concept, then only you can answer reason assertion question. Okay, because they check your internal understanding, right? So that kind of questions you can expect in NEET. Okay, so which are based on lot of understanding, internal understanding of the subject, right? And numerical part, then numbers and all they give me easy, so because so that you can get the numbers they give, so that they can get cancelled easily. Okay, and you can make the calculation very easy in a very easy way, but you should be aware of the concept, right? So let's discuss this. If the question is very simple, okay, and if the uncertainty in position and momentum are equal, got it, then what will be the value of uncertainty in velocity? Then uncertainty in velocity will be, okay, option A, this is option B, option C, and option D. So the question is telling uncertainty in position and momentum are equal. Just apply this and start your calculation. But the calculation, actually you don't have to solve the numbers in general formula. You have to put these values and you have to figure out what is the answer. So what you are getting? Nabila, Maha, any idea?
No.
So that is very simple, much simpler than this above question, okay? But we need to try it in a way in which they have said. What they have said, the uncertainty in position delta x and delta p are equal. Got it. So now if you make them equal, right, put them in the formula of Heisenberg uncertainty principle. Delta x into delta p must be greater than or equal to h upon 4 pi. Clear? And if you take delta
Yeah.
p and delta x to be equal, you can put this delta x equal to delta p. Maha, is it clear what I am trying to do? So
Yes, sir.
you have delta p square. As for the given condition, we are doing this question. It should be equal to h upon 4. So delta p is greater than equal to square root of h upon 4 pi. means 1 upon 2, because 4 will come out of the square root, h upon 5. And delta p is none other than mass into delta velocity. Got it? Are you getting my point? Uncertainty in momentum is
Yes.
because of what? Actually, you can't calculate the momentum because you can't because it is a wave nature. You can't calculate its position. You can't calculate its velocity. There will be some error because so now you can get the final answer. So the question is asking only the uncertainty in velocity, that is going to be greater than equal to 1 upon 2 into mass under root h upon pi. So this is much easier, right? To so because you don't have to struggle with that numerical decimals and all. Okay, and even if they get that numerical question, their data is very easy. Just you need to put the formula right and understand what they are telling. So this is the answer. So answer is going to be option A. Is it clear?
Yes, sir.
Yes.
Okay. So, uh, so I hope you understood it. Right? Very easy. Just you need to calculate it. Right? So let's do one more question. Okay. This is for the actual thing. Okay, for the electron. Mass of the electron is you know already. Normally we take it 9.1 into 10 to the power minus 31 kgs. This is the mass of the electron. Planck's constant also, you know. If they provide you the value of the Planck's constant, then we can't round it off. Okay. We need to take the value which they have given. So the uncertainty in the measurement of velocity, you need to figure out if the uncertainty in position is 0.1 angstrom. Got it? So if that is the uncertainty in position, what is the uncertainty in velocity involved for an electron? So in this case, you need to struggle with the numerical data. You do not have any option. So uncertainty in velocity, it is greater than equal to h upon 4 pi m into uncertainty in position. So you need to put all these data 6.626 into 10 to the power minus 34 divided by This is 0.1 angstrom. So you need to convert it into meters, right, Maha? And Nabila, what is 0.1 angstrom in meters? 0.1 into angstrom is 10 to the power minus 10. Got it? So just you have to struggle with the data. That's what the problem is. So you can just try to figure out quickly that what can be the uh, answers. First, you can divide it, right? You can start your division, that is 3.313, right? Then you can cancel this. This is 10 to the power minus 11, and that is 10 to the power minus 34. So you have to subtract 11, it is minus 30, minus 23, right? Then this you can take this 10 to the power minus 31 in the numerator. Just a second. 10 to the power minus 31 in the numerator, it will become 31 minus 23, so 3.313. 10 to the power 7, 8. So this much you need to calculate. Just you can take approximation as 27.9 into 3 is 27. But while taking the approximation, you should look whether the options are far enough or close enough. Okay. So if the options are too far, means they are having different values. So you can clearly go for assumption. But if they are too close to each other, then taking assumptions is going to cause problems. Okay. So in this case, the actual answer which we are getting is 5.79 because this is going to be less than 1. Okay. Into 10 to the power 6 meter per second. This is the thing which we are getting. So I hope it is clear how to do that. Maha, Nabila, is it clear or not?
Yes.
So now we are going to move towards the quantum mechanical model of an atom. So Nabila, now there is no point of talking about the electron being a particle moving in a fixed orbit, having fixed velocities. We can't, that is not the exact representation of the electron. So we should take into account the wave nature. Got it? We should take into account the wave nature. We should not consider the electron moving in orbit Instead, this is the orbit, which is having a fixed radius. Okay. Electron being a particle moving with a fixed velocity, right? So that model is not going to work. We should think of the electron as a wave. But in my previous example, I told you to assume the wave like this, okay? Just like the wave in the rope. But now, actually, it is not a two-dimensional wave. It is a wave which is like a ball within a ball, okay? Because atoms are spherical. So we should talk about the orbitals. We should not talk about the orbit. Okay, we should talk about the orbital. Orbital represents the area around the nucleus where the wave of electron is present. Are you getting my point? But this is represented by some shaded area. Okay, this is actually a
Yes, sir.
complete wave. Okay, region in which the wave is present. So normally I have represented like this. Okay, that also is incorrect because it is just a flat wave. Atoms are not flat; they are like ball. So they have the wave in the within the. So suppose it is like the wave in the ocean, right? It is not a flat wave like which you see when you move a rope, one end of the rope, okay, up and down. So you have the flat. So you have the whole atom being spherical. So this is the wave, and this is the region where that atom, the wave is being present, and that is known as orbital. Got it?
Yes, sir.
So now we should talk about the orbital. We should not talk about the orbit. And the orbital is the region which encloses the wave of the electron. Okay, this is just one electron. This is not that you have many electrons, just one electron. But we should not consider it moving in a circular path. We should consider it to be present in the form of a wave, in a whole spherical kind of wave around the nucleus. And that region is known as orbital. It doesn't have a fixed radius. It is the region around the nucleus. Okay. Spherical region. So have you understood the difference between orbit and orbital? Little bit difference. Detail we are going to discuss it in the next class. Clear? So let me end the class. Bye bye. Take care. Just go through the NCRT.